Good afternoon, everyone. This is Sadia Zafar from HRAI, and I would like to welcome you to today's session on reducing carbon emissions and operating costs with air-to-water heat pumps. Our presenter, Chris DesRoches, the Applied Product Manager of Mitsubishi Electric Sales Canada, will take a look at how net zero carbon will shift the hydronics market away from fossil fuels and towards air-to-water heat pumps, all the while providing both lower operating costs and lower carbon footprints. You will notice on the control panel of your screen the Q&A feature. Please use the Q&A feature to ask your questions at any time during the webinar. They will be addressed at the end of the session. Also note, this webinar is being recorded and the recording will be sent to you following the session. Now we welcome Chris.
All right, thanks, Sadia. Hi, everyone. Welcome. Thank you to everyone for taking the time out of your busy schedules to be with us today to talk about air-to-water heat pumps. Just to introduce myself, my name is Chris DesRoches. I'm the Applied Product Manager with Mitsubishi Electric Sales Canada. I'm responsible for a line of products coming from Mitsubishi Electric subsidiary called Climate Veneta, who specialize in air-to-water heat pump technologies, which Mitsubishi has launched into Canada now. So for today's presentation, we'll just be talking about the technology very generally. There's some perceptions that we have in our minds about the technology and that it perhaps isn't suitable for the Canadian climate. But we'll go over some of the details today, educate everyone about the technology, and hopefully open some doors to some new possibilities as we seek low carbon solutions. So I just wanted to take a quick moment to recognize that today is Earth Day. So on behalf of Mitsubishi Electric, happy Earth Day to everyone. And I couldn't think of a better topic to be talking about today, given that it's Earth Day. So today what we're going to talk about is air-to-water heat pumps, just technology very generally, how it works. Then we'll get into some details about the Canadian climate. So we'll look at different geographic locations. Some of the climates within Canada are already heat pump markets, while others are emerging markets. From there, we'll talk throughout the presentation with some examples for central plant sizing and design considerations, following into educating people on the call about how to compare heat pump versus natural gas in your design process to make some decisions. And then we'll have some examples about different heat pump technology types, including heat recovery, things like that. So again, the presentation today, because of Mitsubishi, we work with commercial systems for the most part, but I've kind of set up the presentation that it talks about the technology generally, so it applies to residential or commercial buildings. Some of the applications will be more geared towards commercial applications. However, the principles still apply to residential systems, and they're in fact a little bit more simple because residential settings are a bit more simpler than commercial buildings. So anyway, and just for today, for learning objectives, I hope by the end of the presentation that everyone on the call will understand conventional air-to-water heat pump technologies, understand the limitations and how to overcome those challenges when you're implementing this into your designs. Then we'll talk about how to compare in detail heat pump performance to conventional gas boiler technologies to make the best possible decision. And I hope by the end of the presentation today, I can convince everyone, to get rid of the perceptions that you may or may not have in your mind about air-to-water heat pumps not being feasible for the Canadian climate. But really, I just want everyone to see this technology not as something that will completely replace natural gas boilers. The Canadian climate's cold, so that's not necessarily realistic, but we can use energy in smarter and better ways and have a mix of both. So using the heat pump when it makes sense to operate it as a heat pump, and when to switch over to an alternative heat source. Okay, so we'll get right into it now with the technology side of it. So everyone's probably familiar with an air-cooled chiller. So an air-cooled chiller will produce chilled water to use in a building. And in order to do that, you have a compressor and a refrigeration circuit within the machine. And typically what that compressor is doing is, all it's doing is moving heat from one location to another. So in typical air-cooled chillers, in order to produce chilled water to send to the building, we need to move heat from one location to another. And that means that we're basically using the integrated coil on the machine as a heat sink, and we're rejecting heat to the atmosphere. So any heat that we don't want in our building through the chilled water circuit, we're rejecting that outside. Simply put, the air-to-water heat pump is essentially an air-cooled chiller that is run in reverse. So within the machine, there's a 4-way reversing valve, which redirects the flow of refrigerant. So if we look specifically at heating mode for a reversible heat pump, it's the same machine, but that coil that was previously being used as a condenser is now being used as an evaporator. So this means we're extracting heat from the ambient surroundings, and we're moving that heat into a hot water loop to use in our building. So here on the right is just showing the refrigeration cycle. So again, you see the coil on the machine, the evaporator. We're extracting heat, and by using a compressor and inputting work into the system, we're moving heat from one location to another, supplying hot water to our building. In order for us to move heat from one location to another, and specifically in order to extract heat from the ambient surroundings, we need to send refrigerant to the evaporator that's at a colder temperature than what the ambient conditions are. So typically with air-to-water heat pumps, it's the refrigeration itself that will limit the ambient temperatures that you can run the machine down to. So typically in buildings, in the example specifically for a 2-pipe system, typically those systems will have a chiller to use in the summer and a boiler to use in the wintertime. So typically in a 2-pipe changeover system, you're either supplying hot water or chilled water at any given time to all the equipment within the building that's supposed to heat or cool the spaces. So for example, in this example showing some air handlers and fan coil units operating in heating mode. Most modern buildings today have 4-pipe systems where heating and cooling is available year-round. We'll talk about that shortly throughout the presentation, but for now, I just want to go over 2-pipe applications just to look at the heating side of it and understand the limitations associated with it. And from there, you can apply the same principles to different types of systems, different types of heat pumps. So typically, if we have a chiller boiler central plant with an air-to-water heat pump, if such a machine exists that can produce hot water or chilled water, it sounds great in theory to, instead of using a traditional chiller, to use a reversible chiller that can operate in heating mode now and use that in parallel with an auxiliary boiler so that whenever you can run off the heat pump, you supply hot water from the heat pump, and whenever it's too cold or perhaps you're not getting the efficiency that you want from the heat pump, you'll just simply switch over to an auxiliary heat source like a gas boiler. If we're talking about net zero buildings, this doesn't necessarily have to be, net zero carbon buildings, this doesn't necessarily have to be a gas boiler. You could simply put in an electric boiler to eliminate carbon from the building. And also in which case, if you're comparing to an electric boiler, a heat pump, because of the COP, which we'll talk about later, the heat pump will always make sense over a conventional electric resistive heating source. So again, the idea is just taking the heat pump central plant with auxiliary boiler and applying that into similar 2-pipe systems that we have. So it sounds great in theory, so how come we don't see more of these systems around these days? Well, one of the limitations that I kind of touched on and hinted at is the ambient temperature limitations, which we'll talk about in a little bit. For right now, I'll just say the cutout for the technology that is available from Mitsubishi Electric typically cuts out at minus 15 degrees Celsius or 5 degrees Fahrenheit. So typically when someone's considering an air-to-water heat pump, that's usually the first question. Well, what's the coldest temperature I can run the heat pump? And when I say that temperature is minus 15, usually they say, oh, sorry, our design temperature in Toronto is minus 23, so it looks like we can't use your heat pump. And that's generally the consensus and the perception that we all have in our minds, because typically the way we've always done HVAC is we look for a one-size-fits-all solution to apply into our building. But things are changing now with the changing landscape, with carbon emissions a central focus. And whenever you think about traditional heating means, we have fossil fuels to burn to produce heat, but other than that, our other options to produce heat in a low carbon future would be electric resistive heat or some sort of heat pump technology. So typically when you're talking about air source heat pumps because of the ambient temperatures, that's kind of the response I typically get. Sorry, it's too cold for heat pumps in Canada. And so this is a map of just design temperatures according to ASHRAE for various major cities across Canada. So if we start on the West Coast and look at British Columbia, Vancouver, they're already a heat pump market. We'll talk about this later in the presentation as well. But essentially, air-to-water heat pumps are the go-to, and they're well on their way to eliminating natural gas into the buildings. They're ahead of what Ontario is at in terms of those regulations. But then if we look in the prairies, it gets very cold routinely below -30 in the wintertime in the prairies. So obviously that's below the cutout of -15 degrees Celsius. But again, if you look at the number of bin hours where you actually are seeing these colder temperatures according to climates, which we'll look at on the next slide, you'll see that it's not really as bad as it sounds. So typically, if your design temperature is below -15 or -20, you'll need an auxiliary heat source anyway, and that's okay because in a low carbon economy, it's more so about using energy in the best way possible, use the heat pump when it makes sense to, and use auxiliary heat, either an electric or a gas boiler when it's feasible to do so. So if we look specifically at Vancouver, this is weather data that I've gathered over the last 3 years. So in Vancouver, they have a little bit of a milder climate, so it's not necessarily the same comparison that you would make in Quebec or Ontario as an example. And because of this climate, that's one of the reasons why they are a really good heat pump market, because that's their preferred technology, and they're kind of setting the stage for the future for the rest of Canada and setting the expectations of what we'd like to see with heat pump technologies moving forward. So this is a bin hour histogram, basically. So on the left axis for Vancouver, this just shows you the amount of hours that you're spending at any given temperature. So for example, if you look at the green lines, this is actually 2020 data, but for 6 degrees Celsius outside air temperature, there's 600 hours in a year that you spend at that temperature. So if you look at the amount of time where it's below -15 for Vancouver, you'll see that it doesn't get below -8. So if you're using a heat pump technology, you don't necessarily need to worry about an auxiliary heat source. And in fact, what we're seeing in British Columbia is that they're eliminating natural gas boilers from the building, where they, in some cases, they won't even have a backup boiler. So that's a little bit of a different market compared to other parts of Canada. They're a bit blessed with a bit of a milder climate. They don't have harsh winters like we do in Ontario or Quebec. So let's look at other places. This is now looking at Halifax, so on the East Coast. So yeah, their design temperature in Halifax is around -18 or so. And if you look at the number of hours that you're actually spending below -15 in Halifax, last winter it didn't even, this past winter it didn't even go below -15 degrees Celsius outside. If you look at the years before, Halifax has milder winters, so spending very few hours below -15 where you couldn't use some sort of heat pump technology. So just showing here for Halifax, between -10 and +10 degrees Celsius outside air temperature, there's 5,000 hours on average that Halifax sees that temperature. So that's 58% of the total number of hours in the winter that they're spending between -10 and +10. So if you forget about the need to run an auxiliary boiler below -10, you can still cover off a significant portion of the heating hours with air to water heat pump and eliminate the natural gas that you're going to use in a boiler. Similarly, for Montreal, we're starting to get into a bit more harsher climates. Toronto, skipped over a slide here. Toronto, our design temperature is -23, but whenever you look at the actual number of hours where it goes below -15, it's only 44 hours. So even this past winter that we just had in Toronto, there was 1 hour where it was below -15, where you couldn't use some sort of heat pump technology. So as you start to look at some colder climates, you see that you do spend more time at colder temperatures, seeing more and more hours, but there's still a significant majority of the hours where you can still provide useful heat from a heat pump as low as -10 typically, and we'll talk about that, why I picked that number to show you today in a couple slides. But we have the mentality that we need to have a heat source that's going to work at all times under all sets of operating conditions. And now we're also saying that we want it to be low carbon. So we want to have our cake and eat it too a little bit. And this is why I show this data, because whenever you look at the actual number of hours, you'll see that it's not necessarily as big of a deal, and you can overcome this for any designers in the room. You can get around by just having an auxiliary heat source. So again, even in Calgary, it gets very cold below -30, and you do see more hours that are spent below -15 in the Calgary climate. But again, between -10 and +10, there's still over 4,600 hours, 53% of the time that you're spending within that temperature range. So the reason why in the last slides I was showing kind of some different temperatures, showing where the temperature range is below -15, showing the temperature range where it's between -15 and -10, looking at -10 to -5, -5 to +3, +3 to +10, +10 to +20, and above 20. That's really to demonstrate what's referred to as the operating envelope for air-to-water heat pump technologies. So the heat pumps available from Mitsubishi, they can operate continuously down to -15 degrees Celsius. There is another class of this type of equipment available from other manufacturers in Canada that typically will have gas injection compressors that you can achieve a little bit of an extended operating range and operate down a little bit lower, like -20. And even at -20, you might be able to achieve a slightly higher supply temperature. But if we just look at the conventional basic type of air-to-water heat pump for commercial settings, we'll see that our minimum temperature that we can operate the heat pump is -15. But also at -15, depending on the specific model that's selected, you can only really get as high as about 40, maybe 45 degrees, depending on other manufacturers in terms of the supply temperature. So the question and rebuttal I usually get from engineers is, well, we can't really use 35 degrees Celsius as a design temperature in our system to actually meet the heat loads in the building at -15. And while that might be true, there's different systems that you can look at using lower water temperatures, because in the low carbon economy, there's more and more talk about condensing gas boilers becoming the standard in Canada post 2025. And still with air-to-water heat pumps, for import radiant systems, you can still use a lower supply temperature of 35 or 40 degrees. The reason why in the previous slides I was talking about -10 is because this is a common design point in Vancouver where at -10 degrees Celsius outside air temperature, typically from these types of heat pumps, you can still achieve a 45 degrees Celsius supply. So although the cutout's -15, maybe you don't want to operate it below -10 anyway, because maybe you don't have, for convection heat emitters, 35 degrees is probably too cold to get useful heat transfer into the building. But even if you just look at the amount of hours that we went over in the last slides, where it was between -10 and -5, you'll see that you can get different supply temperatures. And for any designers on the call, typically you want to pick a fixed supply temperature for the system. You don't want to have a bunch of different operating conditions. Well, if it's condition A, then I'm going to have a supply temperature of X, but if it's condition B, I'm going to have a supply temperature of Y, and so on. You're going to typically just pick one supply temperature and stick with that. So for the air-to-water heat pump, this is why you will typically just want to look at what's referred to as a bivalence temperature. But again, really one of the other key takeaways from this presentation is to think about heating systems generally and how to incorporate air-to-water heat pumps into those systems. And really, the way you can have the highest efficiencies and a broader operating range with air-to-water heat pumps means that you want to design for the lowest water temperature that is feasible for your design, so that you can have a broader range of time that you can operate the machine and still have a high enough supply temperature that you can meet the heat load in the spaces that you require. So for example, if we look at a 50 degrees Celsius supply, if we look at the operating envelope, we can basically only manage that temperature as low as -5 and as high as about 22 degrees. So again, on the y-axis here, we have leaving water temperature that the air-to-water heat pump can produce according to outside air temperature. So for example, 55 degrees Celsius is the maximum supply water temperature from this type of heat pumps typically. Some of them might be able to do 60 degrees. And it sounds good, but whenever you look at the operating envelope, you'll see that you can only use a 55 degree supply between +3 and +10 degrees Celsius. As it gets colder than 3 degrees Celsius, the maximum leaving water temperature that you can get from the heat pump will decrease. And so will the capacity and COP, which we'll take a look at on some other slides. So again, the operating envelope is kind of key for air-to-water heat pumps, and you need to understand the operating envelopes and the limitations of the technology, so that rather than design a system with a chiller and boiler and then say, okay, well, now what can I get out of the heat pump? The better approach would be to design the system around the heat pump capabilities. Maybe the heat pump doesn't need to supply 100% of the heat for all the systems in the building. Maybe there's some low-grade heat that you can use, depending on the application, to still have usable heat transfer into the building with supply temperatures. So if we just build on that concept of, a 45 degrees Celsius leaving water temperature from the heat pump and -10, this means that if you use a 45 degrees Celsius supply temperature, you can run off the heat pump as low as -10 and as high as about 28 degrees Celsius. Or if you're looking at condenser loop systems or inflow radiant systems, this means that you can use the heat pump from -15 to +40 at all times with a 30-degree supply. So again, just minimizing the design temperature as much as feasible within your design will allow you to take better advantage of the heat pump. So again, just looking at the operating envelope and design point selection, we know that we will have a relationship between outside air temperature and the supply temperature from the heat pump. In addition to this, it's not shown in the diagram, but we'll talk about it in the next slides, is we'll have a capacity reduction as the outside air temperature decreases. So when you approach any manufacturer that offers these heat pumps, whenever they provide you a selection based off your design conditions, so when you tell them the water temperature and the air temperature that you want to run the heat pump down to, they'll provide you a selection that reflects the available capacity at that point in time. But it's important to remember that as it gets warmer, or if you differ from the nominal conditions, your capacity will change. So it's important to understand that and review in the product literature accordingly. So for example, if we look at a winter design temperature that's below -20, we're talking about using an air to water heat pump. We'll simply just switch over to an auxiliary boiler whenever we need water, whenever we need hot water supply below the cutout of the air to water heat pump. But again, for the boiler operation, there's two different ways you can kind of run it. You can size the heat pump to run with the boiler. In those instances, you're still restricted by the limitations of the heat pump. So the heat pump can't provide any heat below -15. And the other limitation that you'd want to watch out for is if you're using a boiler for maybe half the load and the heat pump for the other 50% of the load, you want to make sure that they both have the same supply temperature, because the boiler is not affected by a temperature reduction according to changes in outside air temperature, whereas the heat pump is. So for example, if you had a 55-degree supply, the boiler could do half that load and the heat pump could do the other half of the load. But what's going to happen as it gets colder into the evening later on in that day, eventually for a 55-degree Celsius set point, eventually your heat pump, if the return water temperature is low enough, meaning you have a load, the heat pump can add heat to that, but it still has limitations due to the refrigerant to hit a maximum supply temperature. So for example, in the evening, if it's -10, the maximum leaving water temperature from the heat pump is 45 degrees. The boiler can still provide 55 degrees if it wants to. So you need to take that into account. But it's basically about the return temperature to the heat pump. Depending on the return temperature from the system, if that's above the maximum leaving water temperature from the unit, then the heat pump can't add any heat to it. So if we're looking at auxiliary boilers, because of the heat pump limitation at -15, you'll need an auxiliary boiler to run below that. So you could have a gas boiler or an electric boiler. So the electric boiler, you might want to do that if you're doing a zero carbon building. If you're trying to eliminate natural gas in that building completely, an electric boiler can still meet those design requirements. And then of course, anytime you're able to run off the heat pump instead of the electric boiler, that makes sense from a COP point of view, which we'll talk about in a couple slides. So again, if we look at the design temperature for Toronto at -23, this is the same diagram with the heat pump supply temperature, but also on the right axis now, we're just looking at the building space heating load. Because the other thing to keep in mind with heating systems generally is that your space heating load is going to be at 100% for the design day conditions. So in this example, -23 degrees Celsius in Toronto, that's where at -23, we have 100% of our heating load. And as it gets warmer from our design temperature, we typically have less heat loss from the building, meaning we don't have 100% load. And eventually, as it gets into the warmer temperatures, between 10 and 20 degrees, in a two-pipe system, for example, those will be just changed over. So typically in April or May. It's not necessarily a fixed temperature, but generally, the warmer it is outside, the less heat losses you have. So the less requirement to add heat to the building is required from either a boiler or a heat pump system. So if we look at supply temperature for the system, most of the time when I'm talking to engineers, they'll say, well, 45 degrees Celsius isn't hot enough of a temperature to meet the heat loads in the heat emitters in the building. But it's important to recognize that you're comparing that to a design temperature at a much colder outside air temperature. Because of the relationship between the space heating load and outside air temperature, chances are you don't necessarily still need that same high supply temperature that you're using at minus 23 in this example. And in boiler systems, this is the reason we use outdoor air reset strategies, because as it gets warmer, we don't necessarily have as much heat loss from the building. So we're basically just trying to operate our heat source to match that heat load as it gets warmer outside. So one strategy that you can look at for heat pumps is, if you're sizing heat emitters in the building and you think that, 45 degrees Celsius is too cold to use, you can do a capacity check. You can still select your coils for a hotter supply temperature of, say, 60 degrees Celsius in this example. And as it gets warmer outside, you can decrease the temperature and just verify that you have enough capacity to work with the supply temperature available at the cutout temperature where you want to use the heat pump. So in this example, you check the heat load for the heat emitters at 60 degrees Celsius for your design conditions, verify that you can match the heat load at that operating point. And then for running off the heat pump at minus 10, chances are you have less of a heat load required in the individual spaces, so you can see what capacity you have with a lower water temperature from the heat pump and verify that it'll still meet those needs. And then that means that you can essentially run off the heat pump as long as it's warmer than your design selection point for the heat pump. So that was supply temperature and the operating envelope. And the other consideration that we need to keep in mind is also how the capacity will change over time. So if you look at any air-to-water heat pump manufacturer's literature, we'll publish nominal capacities based off AHRI 550, 590 standard. So whenever a manufacturer publishes standard conditions, this is rating the heat pump with the capacity that's available, typically around 8 degrees Celsius. So if we're looking at our heat pump capacity at 8 degrees Celsius, this is our nominal value. So in this example, this is a 138 kilowatt nominal heat pump. So we have an abundance of capacity available here. And now this curve here on the bottom is our heating load for the building. Now, this is an arbitrary example. Every building will be different. 4-pipe systems might require heating for dehumidification through the summer. But generally, the heat pump capacity will decrease from nominal value. So essentially, you'll have, at the nominal conditions, you'll have an abundance of capacity, and this heating curve might be different in shape, might be higher, lower. But in this example, this would be selecting the heat pump to provide heat to the building at minus 15. So again, with a 35 degree or 40 degree Celsius supply, you can select the heat pump to meet 100% of the design capacity at minus 15. In reality, for Toronto, this line would extend to minus 23 or so with a higher heat load. So generally, if you're looking at, how to optimize the size, you can kind of just consider and look into the detailed specs of the equipment that you're considering to see how the COP will change according to outside air temperature and how the capacity will change according to outside air temperature. And in most cases, what you'll find, even though we can run the heat pump down to minus 15, chances are we'll probably want to switch over at a different outside air temperature, either because the COP is too low, either because of operating costs for an auxiliary gas boiler over a heat pump. It's all subjective and it's all part of the design. And, this is one of the reasons why it's called an applied product. It's not just a magic box that you can put on the roof of your building and supply heat at all times. You really need to understand how the building is going to perform and behave and select the heat pump so that you have the best combination of things. And again, remind yourself of what's the objective here. If you're trying to do net zero carbon designs, then this is the approach that we're going to have to take. So we have more details coming up as well. So again, just bivalence point, that's one of the keywords. Bivalence point just means you're changing over to an auxiliary heat source at a certain temperature. So if we want to further understand the influence of outdoor air temperature and heat pump systems, what's the effect of outdoor air temperature? So we know that we have an operating envelope that we have to understand and we have to deal with and select our temperatures according to this. We also know that our heating capacity and our heating COP are going to fluctuate according to outside air temperature, and typically they'll decrease in curves that look like this. The other thing to keep in mind as well for air to water heat pump systems is, contrary to chillers, if you're gonna have cooling available year round, typically that chiller outside would have glycol in the system, or in some buildings they might drain that system and not operate them during the winter time. With air to water heat pumps, you can size them with glycol, but it's important to recognize that there is a little bit of a performance penalty that you are paying, same as in any HVAC system. With glycol solutions, it inhibits heat transfer, so usually results in higher pumping heads and a little bit less heat transfer from the system. But there are ways around it. For example, heat tracing is common. And continuous pumping is one strategy that can be employed as well. So typically flowing water will not freeze. So that's one strategy that can be used in combination with heat tracing. But it's all really designer's choice. The reason we use glycol is mainly for freeze protection and peace of mind. But it's also important to recognize that whenever your heating system operates in the winter, you'll get that system up to the operating temperature, but then it's going to stay at the supply and return temperatures throughout the winter. We're really just concerned about what happens if there's a power loss. So having pumps on emergency circuits and heat tracing on emergency circuits is one strategy to get around that and have a little bit of a boost in the overall efficiency. The other thing with air to water heat pumps is, or any type of air source heat pump really, is that defrosting cycles are required. So typically with these types of systems, this is showing the heat pump operating in heating mode, where we have a condenser where we're providing hot water to the building, and we're doing this by running a compressor and using an evaporator coil where we're extracting heat from the environment. So in order to extract heat from the outside ambient conditions, we need to supply refrigerant to that coil that's at a temperature colder than it is outside. And what can happen is, if it's damp or moist outside, you can get frost and ice that will actually condense and freeze to the coil because the coil's at a much lower temperature. So the way we manage this in defrost mode is we actually switch the unit into cooling mode. We shut off water flow from the condenser because if our building's in heating mode, we don't want to be cooling the water down in that system. That's counterintuitive to the concept of a heat pump. So we shut off the water flow to the indoor spaces. And we also are now sending hot refrigerant to the condenser coil on the machine, but we're also shutting off the fans. And this is to allow the refrigerant, hot gas, to melt any ice or frost on the exterior of that coil. So typically with defrost, there's kind of two main ways most manufacturers are doing it. There's standard defrost, which is really just based off fixed timers in the control logic for the heat pump. And it's using the evaporating pressure as an indicator of having frost or ice built up on the coil. So basically, if your evaporating pressure on the refrigerant circuit decreases, if it decreases below the program value inside the machine, after a fixed countdown timer, it will eventually say, okay, we need to defrost, and we'll switch the machine into a defrost logic. With fixed timers, it's rudimentary in a sense, and the heat pump doesn't have eyes. It can't really see how much ice or frost is built up on the coil. So it's just using fixed timers and hoping that it melts off all the ice. So if you do have instances where there's a harsh winter and a harsh conditions on a particular day with fixed timers, you might not melt all the ice off the coil. So then it just basically says, okay, well, the next time I'm going to try to do that again. And usually with fixed timers and harsh conditions, it can lead to buildup until eventually someone's going to get a service call about it because the heat pump's not running. There's been a lot of great strides within the industry from a lot of other manufacturers to have variable timing defrost cycles, simply put. So basically, modern defrost cycles will look at the ambient conditions and a few other parameters in the logic that I won't get into right now. If you're interested in that, feel free to reach out after the presentation. But essentially, by modulating the fixed timers, we can optimize our defrost cycles so that we're basically matching the conditions of the day, and we're only defrosting when it's truly required. So this is something to look out for whenever you're doing some selections for heat pumps and understanding the defrost cycles. But typically they'll only last a few minutes, and again, depends on the conditions. So we've covered so far heat pump technology, how it works, what some of the limitations and challenges are. So why would we want to use one of these systems today? In Canada right now, our natural gas prices, they are on the rise due to carbon tax, but they're still a lot lower than what it costs to operate a heat pump. But, you know, we have a carbon tax in Canada that has been upheld as constitutional by the Supreme Court just recently. But that was under the Greenhouse Gas Pollution Pricing Act, which was implemented in 2019, that had a price on carbon of $20 per ton, going up to $50 per ton by 2022. And it was supposed to stay there. But now with the federal government's proposed plan that they announced in December, they want to increase that carbon tax up to $170 per ton by 2030. So whether or not that will translate directly into pricing for the heat pumps is debatable and still in flux at this time. There's a lot of discussion about, you know, if we have a change in government, what's that going to look like? But even surprisingly enough, the Conservative government has come out now with their proposal for a climate action plan of sorts, which is still better than their previous plan, which there was none. But, you know, so it's good. And we're coming to a realization that, you know, we need to use our energy in better ways. And how do we do that? Either from the regulatory point of view, from building codes. You know, Canada wants to be net zero carbon in all of our new buildings post 2030. And there's a lot of work ongoing into updating the building and energy codes so that we can actually get there and mandate the requirements. But still now, even with natural gas pricing still in a bit of flux, there's still a lot of good reasons why you may still want to look at using a heat pump system today. If, you know, the other part with Canada's targets for buildings is that we want to retrofit all the existing buildings in Canada by 2050. So that's still quite a ways away. It's almost 30 years away. But if you put up a building tomorrow with a chiller and boiler, whenever you need to do something about that building before 2050, you know, if you have if you don't build the electrical capacity into the building, then that could pose a problem in the future as well. You know, whenever I go to a job site and go into a mechanical room and I see a bunch of big boilers, you know, the first thing I'm thinking of is, okay, how are we going to get power here to run the heat pumps to offset all this natural gas? So there's a lot of good reasons why you can still look at building resiliency into your systems by having a dual fuel system. So, you know, with air to water heat pump technology, there's limitations to how cold you can run the equipment, -15, -20. It doesn't really matter because in most places in Canada, our design temperature is below -20 anyway. So you need an auxiliary heat source in the building anyway. So you can have an electric boiler if your objective is to eliminate natural gas from the building, or you can have a gas boiler if you're concerned about operating costs. But still with electricity, you can take advantage of time of use pricing and develop a comprehensive energy management strategy on site to decide when and how to run the heat pump versus an auxiliary heat source. But, you know, if you look at one thermal kilowatt hour provided from a heat pump versus a natural gas, is basically a ratio of 5-to-1 for Ontario. So if you are providing one thermal kilowatt hour to the building, it's 5 times cleaner to do that using a heat pump than it is to burn natural gas. And in BC, their electricity is about 16 times cleaner. So there's, you know, these are reasons why the British Columbia market is a heat pump market. But what's also going to happen across Canada is that we're going to make improvements to our power plants, adding more wind and solar into the mix to be able to make cleaner electricity to make sense to run heat pumps. And supposedly with that will also come reductions in costs. Solar is now the cheapest way to produce electricity. So we will be seeing a lot more of that as technologies improve as well with energy storage and things like that. But even on the building code side, you know, there's stricter building codes that are coming into force to basically mandate higher efficiencies. So if we look at carbon emissions from a building, you know, this is the city of Toronto. It's always going to, over time, towards 2030, it's always going to get tighter building envelopes for less heat losses, improving the overall efficiency, and then trying to eliminate carbon from the building. So we see kind of a step code in Toronto that other cities in Canada are also looking at adopting. But it's basically going to mandate towards the end of this decade that we'll be looking at near zero emission buildings. And if the way we've always heated our building is with natural gas, either furnaces or boilers, if we're trying to get natural gas out of the buildings, the only way we can do it is with electric resistive heating and with with a heat pump. But a heat pump, because of the COP, will always make sense over an electric boiler. Cost-wise, electrical sizing for the building, it can be as much as half as much with an air-to-water heat pump. Also, one thing that's also interesting is the city of Vancouver. They have new legislation put in place that starting in 2022, you can't even use natural gas for space heating or domestic hot water. They're requiring that you need to use electric heat pumps to heat or cool the buildings. So there's a lot that's happening on the regulatory side as well that's going to kind of make the case for heat pumps. So how do we compare the two? So if we look at a natural gas boiler and our source input versus a heat pump, for natural gas, we're using natural gas in the boiler, burning that to produce heat. A natural gas boiler or even a furnace will always operate with a maximum efficiency of 100% or less. So typically with condensing gas boilers, these operate with efficiency is typically around 95%. So how do we compare the heat pump to it? So I've said this a couple times throughout the presentation is COP. This stands for coefficient of performance. So coefficient of performance is basically a metric where you look at the heating or cooling capacity that's delivered from a machine and divide it by the power input to give you a coefficient of performance. So typically at nominal conditions for air-to-water heat pumps, the coefficient of performance will be 3. So this means that for 1 unit of electricity or energy that you put into the machine, you get 3 units of thermal heat out from it. So if we're comparing efficiency of a boiler from a pure energy point of view, a heat pump at nominal conditions with the COP of 3 will be 3 times more efficient than its natural gas counterpart. So how do we directly compare the costs of 1 thermal kilowatt hour provided from either natural gas or a heat pump? So a thermal kilowatt hour provided by a boiler is the same as a thermal kilowatt hour provided from a heat pump, but we can equate them to be the same. So if we want to compare the dollars between the two, if we look on the heat pump side, if we look at how much we're paying for 1 kilowatt hour of electricity, so typically average is around 11 cents in Ontario per kilowatt hour. If we divide that by the COP, that's telling us how many dollars we're spending to provide 1 thermal kilowatt hour to the building. Similarly, for a gas boiler, we take our dollars per kilowatt hours of natural gas, whatever the cost is, and we divide it by the efficiency to figure out how much it costs us to supply 1 thermal kilowatt hour provided from the boiler. So we can equate the two together and come up with this equation, and we can rearrange the equation and calculate a break-even COP from the heat pump. So just basically rearranging this equation, you can express the break-even COP not with discrete costs of energy, but with the ratio of cost between electricity to natural gas. So dollars per kilowatt hour electricity divided by dollars per kilowatt hour natural gas times the boiler efficiency will tell us what COP the heat pump needs to operate at in order to be cost neutral. So the same cost to operate a heat pump or a boiler. So then what we can do is we can plot that equation. So I've plotted that equation for different efficiencies for natural gas boilers. So 95%, going down maybe as low as 80% in some older high temperature systems. Again, you'd want to make sure that you're comparing the same supply temperature whenever you're making the comparison. But basically, and the price that I have here for the average price of natural gas I'm using is about 30 cents per cubic meter. If you go on Enbridge's website and look up what the cost is for natural gas, it's actually very complicated, and you need to look at it. You basically look at the bills and look at the total of the bills and look at the total cubic meters that's been used. And you'll find that the actual price that you're paying pre-tax is in the range of 25 to 30 cents per cubic meter. So based off this and an average price of electricity of 12 cents in 2021, what I believe to be the cost ratio is around 3.3. But again, based off the information you have in the designs, take a closer look at it. But basically, this means that if we're comparing it to a 95% efficient boiler, we basically need a COP of 3.2 in order to be cost neutral. But if we're comparing that to an 80% efficient boiler, really we need a COP only of about 2.6 in order to break even. So now how do we compare that to the COP from the heat pump? Well, this is again using the same rates and figuring out that this break-even COP for 2021 is around 3.3. And this is plotted on the right side of the graph. So we're looking at COP here. And basically the COP will be at its maximum value at the warmest temperature because it's easy to extract heat. But then as it gets colder outside, your supply temperature might decrease depending on what you've selected it for. But the COP will also decrease. But the intersection of these two curves will tell us where it's automatically more economical to run a heat pump over a natural gas boiler. And also shown in this graph is just the number of hours, just so you can visualize, but this is the frequency of hours that we're seeing. So the break-even point is around 7 degrees Celsius. And for Toronto in 2019, there was 300 hours that were spent at that. So anytime you're doing heating above that value where the COP is higher than the break-even COP, then this means that it's all operational savings from the heat pump. So again, if we look at the federal carbon charge, this is from Enbridge. In 2019, the carbon tax was at $20 per ton, and this translated into 3.91 cents per cubic meter would go towards the carbon tax. So in April of this year, the price just went up, which put it at about 7.83 cents. And it's going to go up next year again to 9.79 cents per cubic meter of gas. And then the question is, what's going to happen from 2023 to 2030? This is where we're at today, and this is where the government's proposing we go. Whether or not this will translate directly into pricing of increasing the cost, if you project these values towards 2030, you'll see that the price of natural gas will double by 2030. I don't want to create false expectations. I don't have a crystal ball for future energy prices, but it's all subject to what your local energy costs are. And that's why I presented the last chart in terms of the ratio of costs. And I just encourage people to double check, with your utility providers and try to understand the true cost of what you're paying for energy. And the same also goes with electricity. Whenever you add up all the delivery charges and everything on the bill, that's how you get a more accurate sense of what the operating costs are and how they compare to natural gas. But using the equations that I presented previously in this, that will kind of show you how to make the comparison yourself with whatever you believe are your local energy costs. Again, just so that you have the best information to make the decision. So this is just looking at a comparison between air-to-water heat pump and conventional boilers. So typically, this is an example for a two-pipe changeover system. This is also using some approximate rates that I forecasted that I would expect around 2025, because something has to happen to the price of natural gas versus electricity so that heat pumps can be more widely implemented. Maybe part of that will be special electricity rates if you're using a heat pump for heating in large commercial buildings. Who knows? But for this example here, this is just assuming a two-pipe changeover system. So we're only analyzing between -10 and +10. Below -10, the auxiliary boiler works anyway, so it doesn't matter. And in a two-pipe changeover system, you will get higher efficiencies if you are doing heating, between 10 and 20 degrees Celsius, but not to skew the results. So I just looked at -10 to +10. I'm looking at a $20,000 incremental cost of, buying a reversible heat pump chiller instead of a conventional chiller. So whenever you look at that, basically on the carbon side, it's 82% less emissions using the air-to-water heat pump in Ontario because we have very clean electricity. So we've reduced the greenhouse gas emissions in the building by about 82% and showing a payback with those rates from the previous slide within 15 years. But again, depending on where the rates go, you can do the calculation and look at it. Just the other point that I want to remind, we talked before about with air to water heat pumps, designing for the lowest supply temperature possible. So the example that we looked at before with a 45 degrees Celsius supply temperature shows your heat pump COP over outside air temperature like this. But for the same capacity, but using a lower water temperature of 40 degrees, you have a higher efficiency, meaning depending on the number of hours that you're operating at, this translates into higher savings. Just one other note, in boilers, we use outdoor reset. You can do the same thing with heat pumps as well, following the heat loss curve for the building. You can program in, fixed curves within the heat pumps to automatically change your supply temperature according to outside air temperature to enhance energy savings. So in this example here, just by having a curve implemented from 45 degrees, dropping your supply temperature to 39 degrees, from 5 to 15 outside air temperature, you can increase the COP from the heat pump as you do that. So there are ways that you can still implement the technology and further enhance the operation of it instead of a fixed supply temperature at all times. I'm running a little bit short on time, but I'm going to try to cover this last section here in about 5 minutes. But I just wanted to speak briefly about different commercial heat pump types. So commercial air to water heat pumps, and residential air to water heat pumps. Residentially, because I know there's probably some people on the call that are wondering about residential systems. All the same concepts that we talked about in terms of operating envelopes would still apply. So anytime you're looking at a specific heat pump, you need to understand how that machine's going to behave according to outside air temperature. But just very quickly with residential type systems, these are usually packaged systems for residential applications, where it's a little bit of a system approach. So you're able to have space heating and cooling with the appropriate terminal equipment in the building, and also integrate domestic hot water into those systems. So basically in summertime, the heat pump can provide cooling to use with fan coil units inside the house or things like that. And whenever it's met the conditions inside for cooling, it can switch and make hot water to charge a hot water domestic tank. Typically, these types of heat pumps will have internal control logic that will allow priority. So for example, in the morning, if 4 or 5 people get up and have a shower right in a row and you've depleted all the hot water in that tank, there's either schedule or priority that you can assign within the logic of the heat pumps to basically manage that. But point is, it's one system that we put into the house to do the job at all times, which is a little bit easier to do than on the commercial side. Basically with the heat pumps, it's also monoblock as well, so water connections between the outside and inside of the house. So again, this is just showing through a valve to control the domestic hot water production in the tank. Commercial air to water heat pumps are a little bit different, and basically the main takeaway that I want people to take away from this presentation and commercial heat pumps is, there's a reason why we call it an applied product. We have to think a little bit differently about how we design systems to get the best value for that equipment that we're putting into the building. So really designing it in parallel with your project and design requirements, fit the project around the heat pump if you're trying to get a low carbon solution, instead of the other way around of having a building say, okay, now how do I fit this heat pump into the project to get rid of carbon? You'll get the best benefit from the heat pump if you design it alongside with the building and selecting your heat emitters for the building to get the best balance between all the parameters that designers are trying to balance for their clients, like first cost, maintenance, efficiency, and operating costs, and so on. But just really quickly, we'll talk about air to water heat pumps. So everything I've talked about applies to either 2-pipe, 4-pipe, or 6-pipe air to water heat pump systems. Obviously, commercial buildings operate with heating or cooling year round. So, but just looking at 2-pipe changeover system, just to visualize it, if you're using 1 or more heat pumps to meet the capacity at the design selection point, you can have, in summertime, you have 1 or more units to meet the load operating to provide chill water for the building. In wintertime, if you're operating off the heat pumps, you operate off the air source heat pumps, you still have that backup boiler. And then if it's too cold for the cutout, or, because of an energy management strategy, if you want to go for costs, if you don't want to operate the heat pumps below a certain COP, you can just switch over to the auxiliary boiler from there. This is just an example on a project. It was just a chiller boiler 2-pipe changeover system where they wanted to basically look at a heat pump solution. They were designing for a 50-degree supply temperature, and they were going to use an 80-ton condensing unit with a remote evaporator. So whenever they approached us for the project, we said, well, no, use a heat pump chiller instead of that chiller. So basically, we selected 2 units, sized them for cooling. They had 240 kilowatt boilers in the system, but based off the conditions we selected the heat pumps for, we had a total of 215 kilowatts from the heat pumps, whereas their boilers are sized for 280 kilowatts, but we were still able to cover 75% of the heating provided from the heat pump. So again, if you look at and visualize the building load versus outside air temperature, the 280 kilowatts is really at your design temperature in Toronto of minus 23. Since we're looking at using the heat pump here only down to minus 5, chances are the heat load below that at minus 5 is below 75% of the peak heating capacity anyway. So it works well in the system to still offset heat. So basically from minus 5 to whatever temperature they're going to change it over afterwards, it's all savings and eliminating natural gas from the heat pump. Alternatively, you could size them just to meet the total heating requirement, but typically because of the derating capacity with air to water heat pumps, if you do size them for heating, sometimes what can happen is you'll oversize the cooling. So that same example, if you selected them for heating instead, you'd actually have 102 tons of cooling capacity available versus 80 tons that are required. But again, because there's 2 units and the staging and part load operation of them, it can still work well. But this is just a consideration that has to be kept in mind for projects. Sorry, I'm just running a couple minutes behind here, but just to kind of finish off, one example that we've done for energy modeling is we looked at an older building that had a chiller boiler system and said, how do heat pumps fit into this building? So we analyzed a large hotel in Vancouver, Montreal, and Toronto with the same system in all those buildings, basically replacing natural gas as much as possible. So in those examples, the heat pumps were sized to operate in Toronto, Montreal down to minus 10 with a 45-degree-Celsius supply. In Vancouver, the design temperature was minus 7. So that was with a 48-degree supply, according to the operating limits. But basically, for all 3 climates, even though we have the perception that air-to-water heat pumps need to be the one box that heats at all times, in this example, we're only using it down to minus 10. And we actually use them with 3-way valves so that each unit can independently work to the chilled water circuit or to the hot water circuit. And what we found was basically a 50% reduction on average for natural gas, a little bit less in Montreal because they have more harsh winters than Toronto does, but still the energy use intensity. And again, this is the metric that will be flowing into the building codes to kind of mandate intensity of natural gas itself will be mandated to reduce that. So you can still have significant savings in terms of kilowatt hours by using heat pump systems over natural gas. There's heat recovery available in the units as well. Just the only other thing I wanted to cover is, 4-pipe systems are most common. There is a class of heat pumps called 4-pipe simultaneous heating and cooling heat pumps that can provide both hot water and chilled water, performing heat recovery at the same time. Those are typically more expensive. You may not necessarily need that in your building. You might want to look at a chiller with heat recovery. But again, the main point here is to look closely and understand how the building's going to operate and work. And then from there, you can select the best technology to use within your building. Heat recovery is great, but it's only good if you actually have heat to recover in the building and a place to use that heat in the building. So dehumidification in summer and domestic hot water are typical heating loads that we can look at using that recovered heat. There's also a class of heat pumps called, this is just the diagram showing the different heat exchangers inside the units, but basically you can think of them as a machine that produces hot water and or chilled water as needed. And in these types of heat pumps, it's not necessarily a COP that we look at, but a TER, total efficiency ratio. And this is basically the cooling capacity plus the heating capacity divided by the power input. And typically you'll have the highest total efficiency ratio whenever your loads are balanced. So whenever your heating and cooling loads are matched, basically you're not using your condenser coils or fans on the machine, and you're just doing internal heat recovery within the machine and getting higher overall efficiencies. But again, it's proportional to the load profile for the building. There's also 6-pipe system, so those are similar to 4-pipe, but they also have an integrated booster module on the heat pumps for it that you can use 6 pipes throughout the building. So 2 for cooling, 2 for heating, and then another 2 specifically for very high temperature for domestic hot water. So basically any building where you have heat to be recovered or require heating, cooling, and domestic hot water year round are places where you want to use that. So again, just to summarize, what's the best application for air to water heat pump systems? The more creative and outside the box thinking you can do, the more success you'll have with it. But certainly if you have green building certification projects like net zero carbon, LEED, or even more stringent local building energy codes, this is the product that you'll want to look at. Specifically to 2-pipe units, think of the heat pump as an alternative to a traditional chiller and 2-pipe changeover systems to now have the benefit of providing heating in the wintertime whenever that chiller would normally be shut off. But really, anytime you want to reduce CO2 emissions and anytime you want to use less natural gas, air to water heat pumps is one way to go if you're designing systems with boilers. But again, don't think of the heat pump as a silver bullet or a magic box that's going to solve all your problems at all times. Think of it as a steady contributor to overall efficiency for the building when it's practical and efficient to do so, whatever that means to you. So if it's lower operating cost, if it's lower carbon, reliability and maintaining indoor comfort, it's all subjective to whatever the requirements are for the project. So think about the heat pump in that way. But again, the better you can apply the product and integrate it into your building, the higher savings and the more greenhouse gas emissions you can reduce. So thank you, everyone. I apologize for going a couple of minutes over, but it's a lot of content to get into 50 minutes or so. So if anyone has any questions or if you're working on projects, feel free to reach out. Here's my contact information. You can also find information on our website about heat pumps, climateveneta.ca. But other than that, thank you for everyone for taking the time to join, and we can kind of answer some questions now.
Thank you, Chris. This was incredible. We have a couple of questions, but as we are over time, what I'm going to do is I'm going to shoot the questions off to you via email, and then we can respond to the people who asked the questions.
Okay.
Okay.
Perfect.
All right. Okay. So with that, again, thank you, everyone. I hope all of you enjoyed the session and found this informative. If you have any questions, please feel free to reach out to HRAI. Once again, as we went over time, we will be sending, the questions will be addressed after the session and will be sent to you by email. Additionally, please complete the evaluation survey that will appear on your screen at the end of the webinar. And with that, have a great afternoon, everyone. And thanks again, Chris.
All right, thanks, everyone. Anyway, hope to hear from some of you soon. And I'll be getting back to everyone with questions after the webinar. Cheers.
Great. Thanks, Chris. Bye, everyone.